In this video, we'll look at quantum theory and the Bohr model. Niels Bohr adopted Planck's assumption and was able to explain phenomena this way. What Niels Bohr was able to explain was that the electrons in an atom can only occupy certain orbitals, so they can only be of certain energies. Just like how Planck said that energy can only be certain energies, Niels Bohr said the electrons can only occupy certain orbitals. And two, electrons in permitted orbitals have specific allowed energies called stationary states. And these energies will not be radiated from the atom. So you can kind of think of the stationary states almost like the electrons are at a fixed distance from the nucleus. And then three, he said the energy is only absorbed or emitted in such a way that moves electrons from one allowed energy state to another. So that means the energy is either gained or lost as a photon. So when a photon enters an atom, the electron will get excited from one allowed energy level up to another. And then when the electron loses energy, it goes back down in state and releases a photon. So looking at a diagram of the Bohr model, when we're talking about our allowed energies, that would be our n equals 1, n equals 2, 3, 4, up till infinity. So as long as n is a whole number, that is an allowed state. So that's a state the electron can occupy. The ground level, the lowest energy, is n equals 1. Anything higher than n equals 1, we consider all of these excited states. And your electron, when it absorbs a photon, goes from n equals 1, can go up to n equals 2, or it can go up to n equals 3, 4, 5, 6, 10. Doesn't matter. When the electron goes back down in energy, so if it goes from n equals 2 down to n equals 1, it loses a photon. And it's lost energy because it's gone from an excited state back down to its ground state. And one thing to note, when n equals infinity, that's basically saying the electron is not present in the atom anymore. So we can say that the electron has been lost from the atom if it goes to n equals infinity. So I'm sure your next question is, how can we calculate this energy? How much energy does the electron actually have to absorb to go from n equals 1 up to n equals 2? Glad you asked that question. So for us, we can use delta E equals negative H times C times RH, and all of that is multiplied by 1 over n final minus 1 over initial, both of them squared. A lot of things in this. H, we know is Planck's constant. C, we know is the speed of light. So those are two numbers that are fixed already. RH is known as the Rydberg constant. And we'll see a little bit more about the Rydberg equation later on in the video. But the Rydberg constant is 1.097 times 10 to the 7th meters inverse. And then n initial and n final are the initial and final states of your electron. So n initial, if we're starting the ground state, equals 1. And n final, if we go up to our excited state, it can be n equals 2 or n equals 3 or 4, 5, 6, as long as it's a whole number. Now, all of this can be simplified so that we don't have to punch a lot of numbers into our calculator. Since the first three numbers, C, H, and R, are all constants, we can multiply them together, and then we get negative 2.18 times 10 to the negative 18th joules. So if we take those three numbers, H, C, RH, multiply them together, we get that number. Easier to remember, easier to work with. And then we can use 1 over n squared as long as our initial state is 1. So we can use this equation as long as the initial state is n equals 1. If it's not n equals 1, then we'd have to use this part up here, the 1 over n final squared minus 1 over n initial squared. But we can still use this number here, the constants all multiplied together. So now that we have an idea of how to calculate our energies, if we look at them and what it actually means as far as light, because we're talking about light and energy, depending on the way your electron is moving between its levels, we either say it's going to emit energy or absorb energy. So if your electron goes from a higher energy state to a lower one, so any higher energy state can go from n equals 3 to n equals 2. So as long as it goes from higher to lower, we call that an emission. So we'll call that an emission. So the electron has to move from higher to lower. We call it an emission because the electron is releasing energy. It's emitting energy. And it emits that energy as a photon, as a wavelength. And so, for example, on our spectrum here, going from n equals 3 down to n equals 1, releases a photon of the green light wavelength, of the green light energy wavelength. Going from 2 to 1 releases it as a yellow light, as a yellow wave. Going from 3 to 2, that happens to be off the visible spectrum. But we'd still be able to calculate what that energy is using the equation we just saw. And so you can see when we look at an emission spectrum, we only see lines of color for the allowed transitions, for the allowed energy emissions. We don't see lines of color going from, let's say, n equals 2 to n equals 1/2. We pretend there's a 1/2 there. Something like that is not allowed. The electron has to do a full transition between the energy levels. It can't stop halfway. Think of it as you're dropping a ball off the second floor balcony. That's your n equals 2 level, and it's going down to the first floor, n equals 1. Your ball's not going to stop halfway down. It's going to complete its drop. Same thing with the electrons. They complete their drop down to their lower energy level. And so now if we look at an absorption spectrum, we can see in the absorption spectrum that the energy is absorbed by the electron, and the electron goes from a lower energy state up to a higher energy state. So go from the n equals 1 to the n equals 2, or from the n equals 1 up to the n equals 3. We can also go from n equals 1 up to n equals 5. You can go from n equals 3 to n equals 5. Doesn't matter, as long as you're going between two allowed states. Again, if you think about being in an apartment complex and it has different floors, you can go between those different floors with the stairs or with an elevator. Your elevator is going to take you up to a different floor. It takes you to a whole number floor. It doesn't stop halfway and expect you to get out. So your elevator is not going to stop in between the first and second floors and expect you to get out. It's going to go all the way to the second floor. So you can think of our electrons kind of like that, moving between their energy levels. And when you have an absorption, so going from n equals 1 up to 3, you actually end up with a dark band in your absorption spectrum. So the absorption spectrum shows all the colors possible, and then anything with a dark band is what the electron or the atom was able to block, because that's the energy the atom and the electron was absorbing. You can also do it from the 1 to 2. You can see that absorbs right around the orange range. So we don't see we see a dark line around the orange range because the electron is absorbing all that energy going from n equals 1 up to n equals 2. And these sorts of spectra, emission and absorption, are really useful to identify different atoms. And they're used quite often in astronomy when you're looking at stars to figure out the composition of different stars. So you can look at an absorption spectrum from the sun and see which atoms are present in the sun. Or you can look at an absorption spectrum from different stars in the galaxy and see which elements are present in those stars. So looking at this idea of having a spectrum that is continuous, where you see all the colors. So we call a continuous spectrum. We get a continuous spectrum from white light or sunlight. And everybody has seen this. If you look at a rainbow, it's a continuous spectrum of colors on that rainbow. You don't see red and then a blank space and then orange and a blank space and then yellow. Instead, you see it as a continuous spectrum from red all the way down to blue and purple. And everybody's seen rainbows in the sky. You can also get a continuous spectrum if you have light going through a prism. The prism will bend the light and bend the wavelength so you can start to see the different colors. And notice there are no dark spots in our continuous spectrum. Instead, it goes from all the possible colors we can see. Now, the continuous spectrum, not super useful for figuring out what atoms and what elements are present. That's where we use line spectrums. Line spectrums allow us to examine and identify different elements. So with our line spectrum, we can see in it that not all the radiation will be continuous. Instead, you only have certain lines that you can see, or certain dark spots that you can see, depending which type of spectrum you look at. Most of the time in chemistry, we usually look at emission spectrums because it's easier to see the presence of the lines than it is to see the absence. It's much easier to see something where there's only 1, 2, 3, 4, 5 lines versus continuous spectrum and hope you see 5 dark spots. So this happens when a spectrum contains radiation of only specific wavelengths. And this is one way we can identify different elements present or different molecules present in a sample. Looking at the emission spectrum of most of the elements on the periodic table, in this one we go up to element 99. You can see each element has a unique emission spectrum to it. They all look slightly different from each other. This is how we can identify all the different elements on the periodic table, is looking at their emission spectrums. So you can see hydrogen here, kind of hard to tell, but there's some purple, there's our blue, there's a red. You can see lithium only has 2 red lines. Helium, you can see there's more, there's blue, green, yellow, couple reds. Sodium only has a yellow. Magnesium only has green. See gallium, mostly purple. Copper has lots of blues and greens here. So we can see all these different colors here. And you can see each element creates a unique spectrum. So one other use we can have for our line spectrums and kind of knowing which emissions each element has is if you've ever looked at fireworks. Let's say 4th of July. This year, hopefully we can have great 4th of July. And you see fireworks, all the different color fireworks. And they come out in kind of predictable patterns, where for a while they might have a bunch of blue fireworks or a bunch of red, or at the end they'll have a bunch of red, white, and blue all together. You ever wonder how they knew exactly which color it was? How they knew how to make those? And the way they knew how to make them and how to have particular colors is they know what emission each element has. So if you wanted something red and you wanted a lot of red there, you might start using a lot of lithium and might use the lithium for your firework. Or if you wanted a yellow firework, you might go to sodium. Sodium will give you a good yellow firework. Magnesium might give you a green one. So knowing the emission and knowing the color can give you an idea of what color you might get in your firework. And so now going back to Niels Bohr, who created this model of a hydrogen atom. Bohr is able to think and comprehend how the electrons might be in a hydrogen atom. And so he came up with what we call the planetary model. In the planetary model, you have your nucleus, where your proton is, and then each ring heading outwards is where an electron can be. pretty much like the orbits of the planets. So this would be Mercury's orbit, Venus, Earth, Mars, Jupiter, Saturn, and you can keep going out. Uranus, Neptune, Pluto. I still want Pluto to be a planet. But each orbit here is where the electron is allowed to reside. The electron can't be in between the orbits. It has to be on its orbit. And the electron moving between the different orbits is how we get our spectrum. So in a hydrogen model, when the electron goes from n equals 3 down to n equals 2, we get a red line. When the electron goes from n equals 4 down to n equals 2, we get a green line. When it goes from 5 down to 2, get a blue one. And then when it goes from 6 down to 2, that's where we get our violet. Notice how they all go to n equals 2. This happens to just be where the visible light spectrum falls for us, is the energy required to go down to the n equals 2. Down to the n equals 1 would fall off the visible light spectrum, but that does occur. And now back to our calculations and comprehending how we can figure out this energy, how we know the wavelength between those different emissions. And now you may be asking yourself, how do I know which wavelength each emission is going to be? How do I know that going from n equals 3 down to n equals 2 shows up in the red wavelength? How do I know that going from n equals 6 down to n equals 2 gives me a violet color? How do we actually know that? We can calculate it. So if we remember, the energy equals Planck's constant times the speed of light divided by wavelength. That's our wavelength. We can figure out where the wavelength shows up. So we can solve for wavelength to figure for a given energy transition. So I can solve for the wavelength for an energy transition using our Reinberg equation we looked at earlier. So if I take my first equation and my second equation and I combine them together, I can figure out 1 over lambda equals the Reinberg constant times the transition from n initial minus n final. So now I can figure out the exact wavelength for each transition that a hydrogen atom does, for each transition of that electron in the hydrogen atom. So now let's practice this. If I ask you, what is the wavelength of energy that is absorbed when an electron is excited from n equals 2 to n equals 6? So looking at this, I want to know what the wavelength is, so I want to know lambda. I have my initial state, and initial is n equals 2. My final state, and final, is n equals 6. So since I know lambda and I have 2 different states, I can use the Reinberg equation. I can use 1 over lambda equals my Reinberg constant times 1 over n initial squared minus 1 over n final squared. So that means 1 over lambda equals my Reinberg constant of 1.097 times 10 to the 7th inverse meters multiplied by my initial 1 over 2 squared minus my final 1 over 6 squared. So that means 1 over lambda gives me 2.438 times 10 to the 6 meters inverse. So now once I take the inverse of that to figure out lambda, that's going to equal 4.10, 4.102 times 10 to the negative 7th meters. Now, Does this really help us figuring out our wavelengths? Sort of. If we were to think about the way we talk about wavelengths, we always talk about them in nanometers, right? So I want to convert this meters over to nanometers so I kind of have an idea about, is it visible? Is it not visible? Because remember, between 400 and 750 nanometers is visible light. So when I convert this from meters to nanometers, I end up with 410.2 nanometers. So now I know this is a visible light. It shows up at 410. 410 is usually a purple range or violet. Which means we could see this transition. And if we look back at our hydrogen model, look, it shows up at 410, exactly what we calculated. So we can do this between any transition, any energy level. You just have to plug in your N final and N initial. Now, with our Bohr model, this works great. This works great for hydrogen. I can go between any energy level, figure out the wavelength for hydrogen. Only hydrogen. There are limitations to the Bohr model. There is a reason why Niels Bohr studied hydrogen. Hydrogen, as we know, is a very simple system. Hydrogen has one proton and one electron. That's it. That's as simple as we can get. He studied the simplest system. Smart on his part. So when you study the simplest system, you can make a model a little bit easier. This is much easier than if we studied anything else. Even helium becomes a lot more complex because helium has our 2 protons, 2 electrons, and also 2 neutrons. Oops. Which means now you have to worry. Having 2 protons, does that change things? It probably changes the electronics a little bit. Having 2 electrons there. If I have 2 electrons and they get really close to each other, won't they kind of repel? Doesn't that make it a little more complicated? Or what if one electron is on one side of the atom and the other electron is on the other side? Won't that be kind of different than if the 2 electrons are on the same side of the atom? So anything higher than hydrogen becomes a much more complicated system. So the Bohr model can explain the emission spectrum for hydrogen, and it works perfect for hydrogen. Doesn't quite work so perfect for anything else. It doesn't explain why sodium only has 1 emission. Sodium only gives the yellow light. But helium gives 7 emissions. It doesn't explain why that happens. But it explains that hydrogen atom perfectly. It explains how the electrons absorb or emit energy of a certain photon. It explains how photons add that energy to the electrons. So he's able to explain the phenomenon between photons and electron excitation and the color light we see. So this is how we see the light is because of the electrons moving. We've also learned that electrons don't actually move in circular orbits. They have much more complex orbits, and we'll see that later. But with the Bohr model, we can calculate the wavelengths for different hydrogen emissions and different hydrogen spectra lines. So you should be able to calculate the wavelength of any emission, or you should be able to calculate the energy levels